have two researchers from Arizona State University. We have Riana Chatterjee and hopefully Kelly Rains join us from the Lens Lab. And Rihanna will tell you later what LENS stands for. Um, they will focus, or the research focuses on AI-driven accessibility for people with visual impairment. They will present their projects on robotic guide dogs and smart glasses and how these technologies could shape the future of independent navigation and daily living. Rihanna, I don't want to take more time and will give you the mic and go ahead.
Awesome. Happy St. Patrick's Day, everybody. My name is Riana Chatterjee, and I'll be presenting some of the work from the Lens Lab um, in this presentation today. So I'll go ahead and start sharing my screen. Awesome. Are you guys able to see that?
Yes.
Okay, perfect. So again, my name is Riana Chatterjee, and I'm from the Lens Lab. I'm a junior in computer science at Arizona State University, studying computer science and robotics. And this presentation is going to be on some of the innovative technology that is happening in AI right now. So let's go ahead and get started. So currently, the issue is that over 253 million people worldwide live with visual impairments. And out of these 253 million people, many have very limited and reliable ways to navigate about their environments independently and in a safe and reliable way. There are several existing tools out there, but a lot of them do fall short. For example, the white cane detects obstacles but can't tell you exactly what they are. Guide dogs are scarce and take over a decade to train. On top of that, they're unable to see over the shoulder line of many people, and there's a lot of hindering obstacles in the sky, like high tree branches or different types of obstacles that can get in the way. GPS apps work digitally, but they don't detect physical obstacles in real time. And additionally, screen readers don't really work outside of the digital world. The
Rihanna, sorry
gap,
to cut you off. Can you go a bit slower?
of course,
Thank
um,
you.
the gap is that nothing really combines real-time understanding, scene understanding with navigation guidance. So this is the Lens Lab. This project is a continuation of alumni Kelly Rains, who was working on developing smart glasses for the visually impaired. Her methodology similarly used AI technology like vision language models, object detectors like You Only Look Once models, aka YOLO, and depth estimation models. Currently on this project, I'm working under the mentorship of Dr. Ronsalu Senanayake, who unfortunately could not be here today, and also our graduate and PhD students in the lab who make work like this possible. So this is an introduction to our lab. This is a Halloween demonstration that we created. So walking into the room, that's our robotic guide dog. His name is Sparky. He's going to jump forward. There he goes. And now he'll do a little wave for us. Awesome. And now moving on to this humanoid robot. This is our human robot. He's going to do a little bit wait for us and hand us a snack. This is him waving at us. And this is our lab. So what exactly is Genesis? Well, delving into Genesis a little bit more, it is a robotic guide dog that sees, thinks, and speaks to help people with vision loss navigate safely. Essentially, the core pitch is that it warns users about obstacles out loud, like cars, street lamps, and road signs, kind of like a seeing eye dog, like a golden retriever. But it is AI powered and accessible for far more people. So, what is the question that we tested? The robot essentially has two brains. It has a fast brain and a slow brain. The fast brain, aka the one that's kind of AI powered by YOLO, you only look once models, kind of operates instantly. It doesn't explain what obstacles are, but rather spots and detects them like a reflex. The slow brain, on the other hand, understands the scene. It tells you what's there in words and describes the scene semantically. The research question is, when should the robot switch from fast to slow? That essentially is the core of the study that we've conducted at ASU. So, what is the Genesis solution? It is a robotic guide dog powered by AI. So essentially, it sees, understands, and speaks. This is the way that it works. A red, green, blue camera and a depth camera captures the scene at a certain frame per second. Then the you only look once object detector estimates the distance about where you are in the scene. Then an AI model, aka a vision language model, describes the scene in real language, a natural language processing model. So, for example, it will describe that you are in a busy intersection with a road ahead of you, as well as many stoplights and street lamps. Then, the audio output delivers spoken guidance and instructions to the user to navigate about the intersection. It'll tell you, there is a car to the left, move rightwards. Or it'll tell you, there's a car in front of you, stop abruptly. And this real-time aided navigation is what keeps people moving from point A to point B. These four components work together in real time to deliver navigation instructions. So, how did we test it? The methodology, in plain and simple terms, is that we simulated four eye conditions using a virtual reality headset. We then had participants walk with the robot while holding the leash like a guide dog, and each person rated the walk from 1 to 10 on a scale of safety, trustworthiness, and reliable. And then the robot automatically tuned its own settings based on the scores that people gave it. So this is a video demonstration of what it looks like for the robot to see. The green mask is the semantic understanding of the sidewalk, while the yellow is the road in front of it. On the left is a live camera feed with the three AI systems running simultaneously in real time. On the right is a depth map where warm colors like orange and yellow mean close, and cool colors like purple and black mean far away. The you only look once object detector is identifying and localizing multiple objects at once. For example, it's identifying cars, a person, a traffic light, and labeling each one with its own distance and feet. And this is all happening on the live robot camera. So, how did we actually go about testing this? The experiment ran in three phases. Phase one was a vision language model benchmarking. We compared different AI vision language models to find which one gave the most accurate and useful obstacle descriptions. Phase two is a robot simulation. We applied four different eye diseases filters to our camera feed to simulate what a visually impaired person would actually see. Things like macular degeneration, glaucoma, retinitis pigmentosa, and diabetic retinopathy. And phase three are the live hardware trials. I myself put on the virtual reality headset, simulated each condition, held the robot's leash like a guide dog, and walked with it through real obstacle courses, consistently rating how safe and useful the guidance felt after each trial. The goal was to find the sweet spot of where AI kicks in exactly at the right moment and find it where it's not too often and not too rarely, but just right. So this is me walking with the AI guide dog. I currently have my virtual reality headset on, and in this specific picture, I'm simulating glaucoma in the virtual reality headset. On the right is an image of the service dog leash attached to the robot and the harness as well. From here, you could also see that the LiDAR sensors are working and the camera is also attached. So this video shows some live segmentation and classification of the full object detection and AI-powered vision language model pipeline. Now that's a lot of technological words just to say this is exactly what the robot dog is seeing when the camera, the LiDAR, and all the sensors are working together to be able to detect and understand the environment around it. It goes about clearly classifying the people, trash can, sidewalk, tree, and obstacles in front of it. This was also not taken on the walk-in guide dog itself, but rather its 3D depth camera that we use to see the world through. This video shows the robot's camera feed of a real indoor environment. It goes very fast because the robot is operating at a high speed at around 30 frames per second. A computer lab with people, chairs, screens, and bags all within a few feet of each other are visible in the video. Exactly the kind of cluttered space that's hard to navigate without sight. Notice that the chair takes up about 2.6 feet within the frame. Without this system, that's a collision waiting to happen. With it, the robot knows exactly what's there and how close it is before you even get near it. And so, to simulate what actual visually impaired users experience, we programmed 4 custom image shaders onto a virtual reality headset, one for each condition. AMD, or macular degeneration, creates a dark blind spot right in the center of your vision with a wavy distortion around it. So anything you look at directly disappears. Glaucoma gives you a narrow tunnel with only a small circle in the center is clear, and everything around it fades to black. Retinitis pigmentosa is the most extreme. It gives you severe tunnel vision combined with night blindness, so you're essentially looking through a tiny pinhole in the dark. And diabetic retinopathy scatters random dark patches across your field of view with heavy visual noise, so your custom is unpredictable and inconsistent frame to frame. And now each of these 4 conditions is required for the robot to behave differently, which is exactly why a one-size-fits-all threshold for guiding people is not ideal. So this is exactly what it looks like through the virtual reality headset itself. These are real captures from the virtual reality simulation in the same robot room with the same courses, but seen through 4 completely different eyes. AMD in the top left, everything is clear in the center and just disappears into a foggy white blur. So the robot is basically invisible while the cones around it are only barely visible. Diabetic retinopathy on the top right almost looks normal until you notice the dark red noise creeping in and all the vision that flicker and patches out unpredictably. On the bottom left, we can see that glaucoma is there, and it's striking. The room is almost completely dark, and you can only make out the floor and a couple cones if you look directly down. And retinitis pigmentosa is on the bottom right, and it is the most dramatic. You're looking through a tiny circle surrounded by a massive black and white void. You can see maybe 2 or 3 cones at once, and that's about it. What the main takeaway is from this is that each of these conditions demands a fundamentally different navigation strategy. And that's exactly what the robot had to learn. So this is what retinitis pigmentosa looks like. It's a severe peripheral vision loss and it simulates night blindness. Now this is what that looks like in Unity, kind of the foggy white edges and black inner peripheral. This is what age-related macular degeneration looks like. It's a central blind spot and distortion in the center cornea of your eye. And now this is what that simulation looks like in Unity as well. This is what glaucoma looks like. It's a narrow central tunnel of vision where you can only see from the near cornea of your eyes. And now this is what that looks like when we simulated it in virtual reality. Finally, this is what diabetic retinopathy looks like. It's dark patches with heavy visual noise. And now this is what that looks like in virtual reality. And so what we were able to discover is sometimes AI gets it wrong. Object detectors models like YOLO, we found in a case study, misclassified a cat as a vase with a 55% confidence level. Then another AI, the vision language model, looked at the same scene, correctly identified it as a cat, and generated useful navigation guidance. And so in this example, we can demonstrate that the slow brain caught what the fast brain is missing. And so one of the most interesting things that we discovered is that AI, as good as it is, sometimes does get it wrong. And when it does, the vision language model steps in and corrects that in real time. Here are 3 different examples from our trials. In the first case, you only look once object detector looked at the robot's legs and called it a vase with a 55% confidence. This is low enough to trigger a VLM. The vision language model then looked at the same frame and said, cat, navigate gently around the small animal. Although it got the wrong animal, it got the right action. In the second example, the you only look once object detector identifies elephant legs and tells the user to stop carefully around a large obstacle. And in the third, the you only look once calls a person with a 46% confidence, but that person was actually forced legs. Then the vision language model correctly identifies these horse legs and gives a specific directional instruction to navigate around the horse legs at a 45-degree angle. What this demonstrates is that the system degrades gracefully. The AI doesn't always need to be perfect. It just needs to know when it's uncertain and hand off the task to someone smarter. The handoff is what makes the system work. So this example is an example of what it looks like to simulate a you only look once and vision language model in real time. So currently, the model is not able to detect anything until we switch the position of the robot backwards and we can see a tennis ball in the left of the sphere. Then the AI detects a sports ball with around an 87% confidence, and the vision language model gives directions about navigating around it. And so these systems work together in real time to make sure that people can be properly guided with proper navigation instructions and identify all the obstacles around them to be able to move around safely. Now it's back to identifying nothing, but when we move around the position again, we can see that a cat and a horse, as well as a plant, appears in the frame. When you only look once object detectors see these models, we can see that it will now classify it with a object class. And that object class that it detects appears to be a person, but then the vision language model correctly identifies a dog. So we can see that it kind of catches the errors that the AI makes. And now this is what the robot's able to see. Sometimes the you only look once model detects a toilet or an airplane when there's actually a robot. But the vision language model gives clear navigation instructions and clear semantic reasoning that it's actually a robot in a room with a chair and a whiteboard in front of it. So, to measure how well the system is working, after every single trial with the robot, I and me and the members of our lab rated the guidance quality on a scale of 1 to 10. A 1 or 2 meant that the system was unsafe. Either the AI never triggered at all and I got no guidance, or it triggered so constantly that the navigation completely froze. A 3 to 6 meant poor to marginal. Something was happening, but it wasn't reliable or well timed enough to actually feel safe. A 7 or 8 meant good. The system was working, descriptions were useful, and the pauses felt tolerable. And a 9 or 10 meant excellent. The AI kicked in exactly when I needed it, the description was accurate and actionable, and the whole thing felt natural. The goal was to find the threshold setting that consistently lands in the 9 to 10 range for each vision condition for perfect navigation. And this is the hardware that we used. So here's a quick rundown of everything we used to build this. The Unitree go-to is a robot guide dog itself. It's in the top right corner. A quadruped robot about the size of a medium dog that can walk, navigate, and carry hardware. Mounted onto it is a camera, an RGB camera, and depth information is processed here simultaneously at a very high rate. So the robot knows both what it's seeing and how far away things are. Then there's the ROS2 and NAV2 software inside that handles the robot's brain for movement and waypoint following. Essentially, it tells the robot, go left or go right once it sees an obstacle. Then we have the Meta Quest 2 virtual reality headset. This is what I wore during testing to simulate each of the 4 conditions that we just looked at. And finally, this is the onboard AI pipeline, the NVIDIA Jetson, and it combines the AI pipeline for all 3 AI models running in real time. And so we can semantically understand the environment and see everything around us with all of these different types of technologies. And all of this run on the robot itself. There's no cloud or external computer operating at hand here. And so, how did we build this? This shows the key improvements we made from our initial prototype to the final system. First, we cut the cord. The robot started fully wireless, no cables or anything tethering to it, which made real navigation actually possible. Second, we closed the loop. In the early version, the robot would just warn you about the obstacles and verbally, but keep walking and walk straight into them. We fixed this so now it actively steers around the hazards and not just narrates them. Third, we improved our measurement. We built proper tracking to log whether the robot caught every obstacle on its path, so we had real data instead of just impressions. Fourth, we hit our speed target. The system reached 85% detection accuracy, running at a very high rate, which is the threshold for real-time usable performance. That's something that we can deploy onto a paper and publish and have it by in real time. The last two are yellow because they're future work. Number five is expanding to more eye conditions like cataracts, and number six is the big one. Running trials with actual blind and low vision participants instead of me and my lab members in a virtual reality headset. That's the next step to make this research truly validated. And so, what we were able to discover, and the central finding, is that every eye condition needs a different threshold on the robot to perform well. Diabetic retinopathy needed the VLM most frequently, glaucoma needed it the least, and they all landed between 8.2 to 9.5 out of 10 for safety. So now we find how well did the system work. Once the robot found the right setting per condition, all four of these conditions scored between 8 and 9.5 out of 10. Before tuning, scores were as low as 1 to 5. Age-related macular degeneration used the edges to compensate for its blind center. Diabetic retinopathy called for backup most often. Retinitis pigmentosa balanced speed and caution. And glaucoma relied on fast detection alone. Sorry. One second, guys. I choked on my water. All right, moving on. So we found that the robot barely interrupts the condition. During a real walk, the robot only stopped to explain the scene 1.5% of the time.
Rihanna, take your time. Take your time.
My bad, guys.
No worries, no worries. Take your time.
So we saw so we were able to see that the robot only triggered when the slow vision language model was about 1.5% of the time. So we could see it speaks up when it matters, but not constantly. This keeps the experience natural and avoids fatigue. So these are the big takeaways from the experiment. Four things to walk away with. One, eye conditions need personalized settings, not a one-size-fits-all. Two, the right setting pushed scores from nearly zero to nearly perfect. Three, the robot speaks up only when it needs to, so walks actually feel natural. And four, lab simulations are a solid foundation, but real-world testing with actual participants is the next step. All right, thank you all for listening to my presentation and bearing with me through my coughing fit. I'm open to any questions that you all may have.
Thank you very much, Rihanna. This was really interesting and futuristic. It gives us hope and makes us feel, think about so many things. I want to start with Kim, who has her hand raised. Kim, please go ahead, unmute yourself and go ahead.
Thank you. This was excellent. And as a orientation and mobility specialist, I'm fascinated by the data that you provided about the difference in the need for assistance between like diabetic retinopathy and glaucoma and retinitis pigmentosa. Is that presented somewhere in a study or something that we can access professionally?
Yes, I found all of this data in a paper,
Okay.
and it's all written in my thesis dissertation.
Okay.
After the link, I can send you the paper to where all of this is published because that's a great question, and it is based on like valid results.
Yeah, and it's helpful for us as O&M specialists, even outside of the context of using the device, because like how much sometimes it can actually help us make decisions about how much instruction and support to provide and how that might vary among the vision conditions. So thank you very much.
Of course, and yes, I fundamentally agree. It's very important to understand all of these different parts.
Rihanna, you can send me the information and we can pass it on. Kim, I can send it to you and whoever is interested.
Awesome, will do.
Okay. Sandy, can you go next? You're muted, Sandy.
So
Okay. Yeah.
this is fascinating and very futuristic, but I'm wondering about the transition from, you were using one robot to try and help a person simulating different vision conditions. What's your next step to testing it with people? And I'm assuming that people who have a real condition hold the leash of this robot and the robot gives them the appropriate best information for their eye condition. Is that where you're going next?
Yes. So we worked with a school for the blind in Peoria over here. And so we have 5 participants who volunteered to kind of be in the study. And so these participants will essentially just walk with the leash and the guide dog, but we have protocols to make sure that they'll be as safe as possible. We'll have all of them in the same room with the same conditions. Essentially, all they're doing is walking around navigation cones. So essentially what this video shows over here. So as they walk and get guided by the dog, they steer around each obstacle and are guided from point A to point B. But the robot dog has done that trial about, I would say, 2,000 different times. So it knows exactly how to navigate around each obstacle. So there's a very, very high percentage of safety available. But we do also want to see how comfortable and how reliable the navigation instructions are itself so that we can continue to move further in the study and see all of those different things compared on a side-by-side type of basis.
And can I ask a follow-up question?
Go ahead,
course.
Sandy.
So in the futuristic world, would you be able to transfer the detectors to a device that a person is wearing so that they're not tethered to a robot? Or do you need the three? Well, yeah, I guess that's my question.
Yes, of course. So our future direction is actually thinking about working with Apple Watches and delivering haptic guidance. So, for example, when you need to turn left or when you need to turn right, the haptic vibrations would vibrate twice. And then currently, we're also working on a mechanism so when the robot guide tells you to stop, you would have a big red vibration. So like a longer vibration that lasts about 2 to 3 seconds. And so this system could also integrate the operating system into the Apple Watch itself so that you don't need a real robot guide dog. But for some people who prefer like a robot human or dog guide dog human interaction, the guide dog is always available there as well.
Thank you.
Rich, I think you had
Yes.
your hand raised. Maybe.
Yes, I did. My question actually is halfway answered just by the last discussion. But Rihanna, thank you for the very fascinating presentation. My question was going to be tailored or directed towards the interface between the person and the dog. Is it a two-way street? Does the dog provide input to the walker, and does the walker have input that the dog can understand, so that the person's desires or wants are also part of the model for navigation?
Yeah, so that's a term that we coined in the study called codependency. And so the codependency is established because the robot has a LiDAR. And so what the LiDAR does is that it can see a 360 frame of view around everything around it. And so the robot itself can detect the person moving in front of it, backwards, to the side, or any kind of spatial point of view it is around the robot. And so as the person moves, the robot guide dog moves with it. So if it moves to the left, the robot dog moves to the left. If it moves forward, the robot moves forward. And if it stops, the robot will stop as well. And so this communication mechanism between the robot and the person itself is what makes this codependency phenomena real and easy to navigate with. But that is something that we're continuing to refine as well with the navigation instructions themselves. So we're thinking about implementing a prototype with the Apple Watches where the person asks, all right, so I'm at this intersection and I want you to do a whole 360 flip around me to explain exactly what's around me. We're implementing a mechanism where that's possible with the robot, anywhere it is. So the communication mechanism is there.
Any other
All right,
questions
well,
before I ask mine? Rich, go ahead. Sorry.
no. I just wanted to thank you very much for the response, and I have to sign off. So thank you very for your attention or for your.
Of course, thank you for asking.
Rihanna, I have a couple of questions. So the dog is audible, or is it all haptic? Like, does the dog
So
talk?
yes, the dog does talk. There's an
Mhm.
inbuilt speaker inside the robot dog. So every
Mhm.
single vision language model instruction and navigation instruction that
Mhm.
the dog gives, it speaks out loud. So for
Mhm.
example, if we are leaving my apartment and going to the store and the robot dog attacks a skateboard rider right in front of me, it will stop in real time and speak to me and say, there's a person navigating with a skateboard right in front of you. Be very careful and steer towards the left.
Oh. Is it Bluetooth compatible? Like if somebody's wearing hearing aids, would the voice go to the hearing aids?
Yes, inside the robot's operating system, you can connect any sort of device, whether it's like a watch, a Bluetooth hearing vision device, any
Mhm.
sort of like smart technology you can connect to the robot.
Wow. Any questions? And oh, can the dog, can you look at I think we have few in the chat.
Oh, yes, I see them now. So
Mhm.
can the robot detect negative objects such as curbs frothing off? Yes, the robot can detect like differences in the environment. So if you go from a stable, dry land to like a wet, muggy territory, the robot will announce that you're about to step onto a very damp, wet, and muggy environment. And then the next question is, can the dog dent traffic lights red or green? Detect. Um, so the robot camera operates with a red, blue, green camera, so it could detect all the colors of every single intersection. And so when there's a red light, it will tell you to stop. And when there's a green light, the vision language model can detect that that's a go sign, so it will tell you to go. Hmm. Does it use GPS so you could ask it to take you to a specific place like a certain store? So not yet does it use GPS, but that is something we're working on integrating in the back end of the code. So currently we have like a whole API, like we have all the systems running. We have
Mhm.
all the hosts trying to connect to the robot and make this GPS system possible. But yes, that is the next step.
Wow, this was amazing, Rihanna, honestly. We had another speaker, but apparently she couldn't join us. And she was going to present on smart glasses. Rihanna, do you have any update on these glasses? I know it's not what you're researching, but anything you can tell us about it? I emailed Kelly, by the way, but I haven't heard back from her.
Yeah, so Kelly graduated last year from ASU, and when she graduated, she passed me her thesis dissertation. So I can share some of her thesis dissertation um, over here. Let me know if you guys are able to see this.
Rihanna, I think most of us would not be. I mean, I
Oh,
can see the
sorry.
screen, but we can treat it. So you can just, briefly tell us maybe what you worked on so we have an idea.
Of course. So
Okay.
Kelly worked on the Ray-Ban Meta smart glasses. And
Mhm.
so what she did, she put AI inside of the Ray-Ban smart Meta glasses. So she put an object detector named YOLO, the same YOLO model that I worked with in my presentation. So inside the smart glasses, the AI could see everything around it. It could see a liquor store, it could see a Starbucks, it could see a busy intersection. And as you walk with the smart glasses, she also put in a depth estimation AI so that the AI could detect how far away each obstacle and each object was. And then it had an inbuilt speaker inside the glasses. So as you were walking with the glasses, the speaker would read out loud what was happening around you and provide image to speech recognition. So This image kind of shows how that system works. So the Ray-Ban smart meta glasses capture the user's surroundings. Then it provides the images of surroundings to the tool. So the AI tool then detects everything around it. Then the AI tool runs depth estimation with the MIDA's AI sensor. And then it returns the annotated images with the desired values into the smart meta glasses so that people could see with them. And so this is kind of the navigation system that she had going with these smart glasses. And when you send the email, I could also send her thesis dissertation in case anyone is interested in finding out more or reading more about generative AI aided navigation for the visually impaired. But her work did work a lot with kind of Ray-Ban smart glasses. And so very wearable technology here.
That's amazing. And it seems this is where the future is going. Tony, please go ahead.
Yes, when you say that she added these AI models into the Meta Smart glasses, I'm guessing you're talking about on board, no external connections like the dog.
Yes, no external connections. All of these were on board.
I'm surprised there's that much processing power in a pair of glasses, but I guess I'm old school.
I agree. I think it had an onboard operating system that was able to handle all of these AI components. I know that the Meta smart glasses, they're about $200. They also have a onboard operating system that allows you to record your environment and see like text to speech and all of those different types of things happening around you. So it's very, very insane what sophisticated AI technology can do these days.
Tony, do you have another question?
No, I thought I put my hand down, but maybe I didn't.
No worries. We'll put your hand down for you. Okay. Any other questions for Riana? Riana, you did a great job. Honestly, thank you for introducing us to the future. And we all look forward to the results of your research. And if there's any way, I personally, I'm sure others would be interested as well in helping out, maybe trying out the robotic dog in DC or Virginia or Maryland. Yeah, I don't mind being a guinea pig and trying it out. And thank you for, just putting you on the spot, being alone on the presentation.
Of course, it was very fun to present to you guys. I love the questions that you guys have.
And thank you all for joining us. Sorry that we're finishing early today, but I think, Riana, you just made our day today. Thank you all for joining.
Thank you guys all for attending. Have an amazing St. Patrick's Day.
Take care, everyone.
Thank you.
Thank you.
Bye. Bye.